In the GNW model, consciousness occurs when information is broadcast across a specific neural network. The speed and success of this broadcast depend on factors like synaptic strength, neural firing rates, and the overall connectivity of the workspace, not the mass of the microtubules inside the neurons. Changing the isotopic composition of tubulin should not affect any of these parameters. The neurons will still fire, the signals will still propagate, and the information will still be broadcast. Therefore, GNW predicts that the gamma band frequency and any other neural correlate of consciousness should remain completely unchanged between the control and the isotope-heavy subject. The result should be mass invariant. Similarly, for integrated information theory, consciousness corresponds to the value of phi, a measure of a system's causal irreducibility. This value is determined by the system's architecture, the intricate web of cause and effect among its components. While a massive change in mass could theoretically alter signal propagation times, the subtle shift from isotopic labeling is designed to be negligible in this regard. The causal structure of the neural network remains identical. The same neurons are connected to the same partners with the same strengths. Therefore, the integrated information, phi, should not change. IIT, like GNW, predicts a null result. The experiment should show no difference in the neural signatures of consciousness. This null result would be just as profound as a positive one. If a carefully conducted experiment with sufficient power to detect a small effect shows no frequency shift, it would be a major blow to the OR hypothesis. It would strongly support the computationalist viewpoint, suggesting that we are on the right track when we model the brain as a complex biological computer. The burden of proof would fall squarely back on those who claim that new physics is required to explain the mind. The mass invariance test thus creates a perfect fork in the road. One path leads to a revolution in physics and neuroscience, the other reinforces the foundations of modern AI and cognitive science. Before we rush to the lab to run our mass invariance test, we really have to confront the towering objection that has faced the OR theory since its inception. This is the decoherence argument, often summed up with the evocative phrase, "The brain is just too warm, wet, and noisy to support the delicate quantum phenomena that OR requires." Quantum states, like the superpositions proposed to exist in microtubules, are, well, notoriously fragile. A single stray photon, a thermal vibration, or even a collision with a water molecule can be enough to destroy the quantum coherence, collapsing the superposition into a classical state prematurely and randomly. This process, known as environmental decoherence, is honestly the bane of quantum computing. Critics, most notably the physicist Max Tegmark, have performed calculations suggesting that the decoherence timescale inside a neuron would be astonishingly fast, on the order of femtoseconds or even faster. That's millions of times shorter than the 25 millisecond timescale OR requires for its gravity-induced collapse to correspond with 40 Hz gamma waves. If these calculations are correct, any quantum superposition in a tubulin protein would be destroyed by the chaotic thermal environment of the cell almost instantly. It would be like trying to hear a whisper in the middle of a rock concert. The quantum signal would just be drowned out by classical noise long before it could ever grow large enough to be orchestrated or reach the Penrose gravitational threshold. This argument strikes right at the very heart of the theory's biological plausibility.